In this video, we are continuing our final exam review by looking at a Lagrange multipliers example. So the question says, define the maximum and minimum values of f of x comma y equals x to the third over 3 plus 4x plus y squared given 2x squared plus y squared equals 18. So I want to begin by letting you all try the problem. So pause the video for at least 6 minutes to try this question first. 4, 3, 2, 1, pause the video. Pause it for at least 6 minutes to try this. All right, so let's talk about it together. So I want to begin this Lagrange multipliers question. And I can use Lagrange because I have this objective equation f that I'm trying to maximize or minimize. And I have this constraint equation where this expression equals 18. So when I do Lagrange, I want to move the terms around to get one side equal to 0. 2x squared plus y squared minus 18 equals 0. And when I do that, this function on the non-zero side, we call it g. So now we want to construct our Lagrangian function. Okay, so we call this L of x comma y. And remember the general formula for L. We take f and then minus lambda times g. So let's write f first. It is x cubed over 3 plus 4x plus y squared. Then I do that minus lambda times g, 2x squared plus y squared minus 18. Okay, so if I distribute the minus lambda to simplify, we'll get minus 2 lambda x squared minus lambda y squared plus 18 lambda. So after we construct our Lagrangian, then we want to find its critical points. So we will take some partial derivatives with respect to x and with respect to y and set those equal to 0. So taking the partial with respect to x, of the first term gives x squared, second term gives me plus 4, and the third term is 0 because there's no x's in it, and then out of the last 3 terms, I'll just be left with minus 4 lambda x, and I set that equal to 0 to find critical points. For the partial with respect to y, from the first 3 terms, I'll be left with 2y. From the last 3 terms, I will get minus 2 lambda y, and I set that equal to 0. All right, so I have my first equation, my second equation, and I need a third equation, which comes from the constraint, which remember was, what was it? It was, right, 2x squared plus y squared equals 18. All right, so now I have to solve this system of equations. Okay, so looking at my first 2 equations, I think the second equation looks easier because it has 1 fewer term. So from that second equation, notice that I can factor out 2y. And if I factor it out, I'll be left with 1 minus lambda equals 0. Remember that when we solve these systems of equations, we never want to divide and cancel away a variable. If I were to divide both sides by y, I would lose a solution. Okay, so luckily we haven't done that. We just factored it out. Okay, so now that it's factored, from this first factor, the 2y, I get that y can be 0. And then from the second factor, the 1 minus lambda, I get that lambda could be equal to 1. So we get these 2 cases. So we have these 2 cases to consider. So in the first case where y equals 0, let's plug this into equation 3 to get 2x squared plus 0 squared for y squared equals 18. So this gives me x squared equals 18, or whoops, sorry, x squared equals 9 when I divide by 2, and then square rooting, we get x equals plus or minus 3. All right, so in this case where y equals 0, we're getting 2 values for what x could be. So we are ready to move on to our other case where lambda equals 1. So if I know lambda, I can, well, the only other equation that has lambda in it is the first one. So let's plug this into equation 1 to get x squared plus 4 minus 4 lambda x, so 4 times 1 times x equals 0. So this is x squared, if I rearrange it, minus 4x plus 4 equals 0. And that factors really nicely. This is just x minus 2 squared equals 0. And from this I can see, oh, x is definitely 2. So now I know my x value, and I could plug that into equation 3 to find my y value. So actually, I'm running out of room here a little bit. Let's do it on the side. Let's plug it into equation 3. That'll give us 2 times 2 squared plus y squared equals 18. If I rearrange this, we'll get y squared equals 10. And if I square root, we'll get y equals plus or minus square root of 10. All right, so in the case where lambda equals 1, I'm getting that x is 2, and x equals 2 corresponds to two y values, positive root 10 and negative root 10. So overall, in each of these cases, the y equals 0 case and the lambda equals 1 case, we're getting 2 critical points. So to organize my work, I'm going to keep track of all the critical points and what I get when I plug them into f. So when y was 0, we were getting 2 possible values for x, 3 and negative 3. And in the other case, when lambda equals 1, we got that x had to be 2, but for y, we had 2 possibilities, either root 10 or negative root 10. So now I need to plug all of these into the function f. So I've gone ahead and done that already. If I plug in the first point, 3, 0, I get 21 when I plug that into f. For the next critical point, I get negative 21. For the next one, I get 62 over 3. And for the last one, I also get 62 over 3. So when we do Lagrange and we get multiple critical points like this, the largest possible output that we get, that is our max. And the smallest possible output that we get, that is going to be our min. So I can definitely see that negative 21 is going to be the min because it's the only negative number. And to compare the others, let's get a common denominator. 21, if I multiply the top and the bottom by 3, is 63 over 3. So that's really close to the others, but a little bigger. So that means 21, this was our max value. So let's write our conclusion, which is the max value. When a question says values, it's asking about the outputs. The max value is 21, and the min value, the smallest possible output, is negative 21. This question did not ask me to write down where they occur, but if I needed to write down where they occur, I would say that the max occurs at 3, 0, and the min occurs at negative 3, 0.